Continuing on our discussion of boiler operation from the previous module, we'll now look at various aspects of boiler control. This will include an examination of that very important feature of boiler operation, boiler water control and conditioning. We'll also discuss environmental factors and control of boiler emissions and effluents. But first, let's take a look at the control devices that permit the operator to run the boiler as efficiently as possible while responding to changes in load demand. We have already studied monitoring equipment, both the traditional control panel and the modern operator's console. In either case, the operator is able to stop and start equipment and make adjustments remotely, that is, from his central operating position. The operator can also manually adjust all of the major operating parameters, such as fuel input, combustion air, feed water flow, steam temperature, and so on. Of course, it's almost impossible to simultaneously control all of the many variables manually. Indeed, it is essential that the major operating variables be controlled automatically. Modern automatic control systems have been developed to a high degree of precision and can provide excellent results in maintaining a high level of efficiency, reliability, and safety. This schematic shows the essential components of a control loop. They are the sensor, transmitter, controller, and actuator. The sensor measures the operating parameter that is being controlled, such as pressure, temperature, flow, or level. This information is then fed into the transmitter, which prepares the signal for transfer to the controller. Older installations still use compressed air as the signal medium. Typically, the pressure of the pneumatic signal will vary between 5 and 30 psi, depending upon the value to be transmitted. Another method for information transfer is via electrical signals, with the transmitter output being adjusted by millivolts or milliamps. These pneumatic or electric signals are known as analog signals. In modern installations, a transmitter produces digital signals for transfer to the computer or central processing unit in the control room. The digital signals have the advantage of being faster and being able to transmit a higher volume of information. Another advantage of the digital control system is its ability to continuously check incoming readings for accuracy and abnormal indications. It does this by comparing multiple readings, computing averages and implied values, so that any obviously incorrect signal is discarded before it can bring about faulty positioning of the auto controls. So returning to our schematic, the sensor signal is fed into the controller, where it is compared with a set point established by the operator. Where any deviation is present, the controller sends an action signal to the actuator to make corrections. The actuator is really the power device in the system, converting small analog or digital signals into mechanical movement. For example, to adjust the fan dampers or to open the feed water control valve. The actuators generally are motivated by compressed air or precisely controlled electric motors and positioners. Even when we're operating the system manually, the actuators are still required to adjust equipment position. In fact, the changeover from automatic to manual control merely allows the operator to provide the driving signal to the actuator and thus enables remote operation. So let's take a look at some typical control circuits. Here we'll simply be looking at the logic of the circuit. The actual control system may be pneumatic, electrical, or digital, but the logic of the operation is the same. Here we see a very basic combustion control scheme for controlling boiler main steam pressure. The actual measured pressure is compared in the master controller with the selected set point. Any deviation causes a correction signal to be sent to the fuel supply actuator and the combustion air actuator. During load changes, the signals are biased so that sufficient combustion air is always available to avoid the potential formation of a rich, explosive mixture in the furnace. For example, during a load increase, the airflow is increased before fuel is increased. The reverse applies during a load decrease. Either of the actuators can be switched from automatic to manual operation if required. An additional control allows the operator to set the desired fuel-air ratio. Experience proves that more excess air is required at low loads to maintain stable combustion. One disadvantage of this simple system is that it must wait for the pressure to actually fall before commencing a corrective action. And even then, some more delay is experienced in mechanically changing the airflow and fuel supply. Yet further delay is encountered before the increased combustion brings about the desired rise in pressure. The cumulative delay from this control system results in a fluctuating steam pressure. This situation can be vastly improved by adding a second element to the control system. That is, by measuring the steam flow from the boiler and using this as an anticipatory signal. We know that increased steam flow from the boiler will result in a falling steam pressure within a time period of about 10 or 15 seconds. However, by applying the steam flow signal to the master controller, the corrective action is started in advance, and so provides increased combustion at about the same time as the pressure begins to fall. The actual resultant pressure then trims the controller settings. A further improvement of the system may be obtained by connecting the oxygen analyzer signal to automatically adjust the fuel-air ratio. This acts as a trimming device to precisely control the combustion air and bring the excess oxygen in the flue gas to the desired set point. Auto control of induced draft, where fitted, is not usually considered part of the combustion control system, as it is operated by a separate, dedicated control loop. The controlling parameter is measurement of furnace pressure, that is, negative pressure. The controller is set to maintain about minus 0.5 inches water gauge in the furnace, and it achieves this by adjustment of the ID fan dampers. Steam temperature control is also independent of the combustion control system. Final and reheat steam temperatures are measured and processed through a controller to actuate one or more attemperating devices such as adjusting the flow of de-superheating water, adjusting the tilt of the burners, adjusting the flow of gas recirculation. This last technique provides the same effect as firing with increased excess air, but without the increased heat loss up the chimney. The recirculating gas merely circulates in a closed loop, while increasing the mass of gas flow across the superheater tubes, with consequent increase in main steam and reheat temperatures. Now, there are many other arrangements of combustion control systems with increasing degrees of complexity and sophistication. You must make sure to thoroughly learn your own system. Another multi-element control system that is vitally important is the boiler feed water control system. The three elements include the actual level of water in the drum, the steam flow out from the boiler, the feed water flow into the boiler. In this arrangement, the level signal tries to adjust the feed water control valve to maintain a constant level. At the same time, the difference between steam flow out and feed water flow in acts as an anticipatory signal so as to provide anticipatory action on the control valve. In some control systems, the set point value of desired water level is automatically adjusted with load, that is, steam flow out of the boiler. At high load, the target level is maintained slightly higher in anticipation of a possible load rejection, with consequent rapid fall in level due to shrinkage. Conversely, at low load, the set point is adjusted to maintain a slightly lower level in the drum, in this case anticipating the possibility of a sudden increase in steam demand, with resultant increase in water level. Another refinement to the feed water control system may be made to the mode of measuring water level. This measurement in inches or centimeters is usually inferred from the pressure indicated at the bottom of the column of water. The problem with this technique is that the density of water in the drum changes with variation in saturation temperature, and this depends upon pressure. In order to improve accuracy, the drum level measurement is corrected for pressure variation by adding a pressure signal to the computation. Yet further refinements may be made to the water level control system, such as steam temperature compensation to provide more accurate measurement of steam flow, compensation for blowdown and soot-blowing steam flow when comparing output steam flow to input feedwater flow. You must make sure to thoroughly learn the automatic control systems installed on your boilers. One very important feature of any control system is that it must provide smooth transfer from automatic to manual operation and vice versa. In most systems, this is achieved by making the alternative selection continuously follow the actual output signals to the actuators. In this case, any switching from automatic to manual, for example, will keep the actuator in the same position till further change is made. Our discussion here of automatic boiler controls has centered around modulating control systems, which continuously adjust fuel, air, feed water, etc., to maintain the desired operating parameters. The actual on-off actions for placing burners in service and monitoring for safe combustion conditions are carried out by the burner management system, as discussed in the previous module. Well, at this point, it's time for us to take a break. We'll come back and talk about boiler water control and conditioning. For now, please switch off the tape and thoroughly review this material in your workbook. When we're speaking of water control here, we're referring not to the water level control, but rather to the quality of water which is contained in the boiler. We already know that a special water treatment plant, including demineralizers and other equipment, is installed in order to ensure that water which is fed into the boiler is super pure. Additionally, certain chemicals are injected into the boiler drum to further control the chemical condition of the boiler water. So what is it exactly that we are protecting the boiler against? What are the problems that can arise as a result of feeding impure water into the boiler? Well, the principal problems arising from poor water conditioning are the formation of scale and deposits inside boiler tubes, the carryover of water with the steam, internal corrosion causing wastage of boiler tubes. Let's take a closer look at each of these items. First, the problem of scale. As much as we try to provide perfectly pure water to the boiler, it is inevitable that some small quantity of contaminants do get through and concentrate in the boiler water as more and more steam is evaporated. Remember, as water evaporates into steam, the solids contained in the water remain behind, and this concentration increases as more and more steam evaporates. This is the situation which occurs in the boiler. Generally speaking, the contaminants consist of magnesium and calcium salts, which are dissolved in the water and contribute to hardness, silica, the products of corrosion of the boiler itself and the feedwater system, mainly iron and copper. At high temperatures, such as encountered in boiler water, and above a certain concentration, these solid materials precipitate out of solution and deposit on the inside of the tube wall. This deposit then forms an extremely hard scale that cannot be removed by the flow of water. The scale acts as a partial insulator of heat and so prevents adequate cooling of the boiler tube by the flow of water passing through the tube. The result is that the temperature of the tube wall metal rises significantly, and in certain zones of the boiler where the radiant heat transfer is at its highest, overheating of the boiler tube metal takes place. The eventual result of this is a failure of the metallic structure with consequent rupture of the tube. Where boiler water contains a high concentration of solids, you should expect frequent tube failures with the resultant need to take the boiler out of service for repairs. In order to prevent this problem as far as possible, limits are established on the allowable concentration of solids that may be contained in the boiler water. This table indicates limits for both dissolved solids and suspended solids. The problem of scaling is aggravated at higher steam pressure because of the higher saturation temperature of the water. Therefore, as we see here, the permitted limit of concentration is much lower when the boiler operates at higher steam pressure. But how can we reduce the concentration of solids? Well, one method is by continuous blowdown. That is, a regulated quantity of water discharged from the bottom of the drum to waste. A control valve is fitted to allow us to regulate the quantity of continuous blowdown. But how can this reduce the concentration of solids in the boiler water? Well, remember, the blowdown water may contain 500 parts per million of solids, and this is replaced by boiler feed water, which contains perhaps 5 ppm. The result then is dilution, with a consequent reduction in total solids concentration. As the blowdown water is at relatively high temperature, between 400 and 500 degrees Fahrenheit, it is discharged into a blowdown tank. This permits some of the high temperature water to flash off into steam and to be vented to atmosphere. The remaining water is then discharged to waste. Of course, there are some losses involved in discharging blowdown to waste. First, there is the loss of heat contained in the water, and secondly, the loss of water itself with consequent increase in makeup requirements. Actually, the best way of keeping the solids content of boiler water at a low level is by maintaining control over boiler feed water and its makeup. The actual limits established for boiler feed water contaminants depend upon the particular boiler operating pressure and temperature and operating regime. However, we would typically expect to find the following analysis of boiler feed water and makeup. These concentrations are given in parts per million ppm. Total dissolved solids are less than 5 ppm. Silica is below 0.15 ppm. Alkalinity is 2 ppm or less. Hardness, as calcium carbonate, is at 2 ppm or less. Feed water may also contain some products of corrosion from the condensate and feed water system. This usually consists of particles of iron and copper which are dissolved into the water stream from pipework and heat exchangers. All of this material ends up in the boiler and increases the concentration of solids. The target limit for copper and iron in feed water is usually established at 10 parts per billion or less. We'll be talking more about corrosion later in this module. Even with all of these precautions and controls, there is still a tendency for the concentration of solids to build up in the boiler water. For this reason, an attempt is made to prevent scale formation by injecting a chemical dispersant such as phosphate into the boiler water. This is usually added at the boiler drum, so a high-pressure pump is required. Phosphate has the effect of keeping the magnesium and calcium precipitate in suspension by dispersing the solid particles throughout the water. The result then is that instead of forming a hard scale, the solids remain as a slurry to be discharged from the boiler through the continuous blowdown line. The addition of trisodium or disodium phosphate to the boiler water does have some negative aspects. For one, it adds yet further solids to the water. In addition to this, it will affect the pH value of the water, and this may aggravate corrosion. We'll discuss this later. Another problem associated with high solids content in boiler water is carryover. The effect of the dissolved and suspended solids is to increase foaming on the surface of the water in the drum. This in turn leads to carryover of water with the steam. Carryover may also be caused by fluctuating water level in the drum or a persistent high water level. High alkalinity in the boiler water may also contribute to carryover. The result is that water is carried on through the superheater, possibly depositing solids and forming scale on the inside of the superheater tubes. The water droplets may also pass along with the steam into the turbine. Here, the water and solids material can cause considerable damage when striking the rapidly rotating turbine blades. We've mentioned that silica may be one of the contaminants contained in the boiler water. This has a rather special effect. At the high temperatures encountered with high-pressure operation, the silica actually vaporizes into a gas and passes over with the steam right through the superheater and onto the turbine. As the steam and silica mixture reach the lower pressure stages of the turbine, the temperature decreases and the silica vapor returns to its solid state. This material deposits on the turbine blades in the form of a very hard, glass-like scale. Silica, of course, is the material which we find in sand and is used as the main ingredient in making glass. The silica deposit on turbine blades is just as hard as glass and extremely difficult to remove. The effect on an operating turbine is to change the profile of the blades and severely decrease the efficiency of the turbine, as well as reducing the output. The only cure is to shut down the turbine, remove the rotor, and mechanically clean the blades, usually by erosive blasting with a material such as aluminum oxide. In order to prevent these deposits, it is most important to keep the silica content of the boiler water below a predetermined limit, typically 5 ppm on a 1200 psi boiler. But how can we reduce the silica content if it is higher than this? Well, one way of reducing silica content is to increase the continuous blowdown from the boiler drum. This is not a very efficient procedure because we are wasting heat and water, but it may be the only solution. If possible, a far better method is to eliminate or reduce to a very low level the amount of silica which enters the boiler with the feed water. In order to achieve this condition, we need particularly high-quality water treatment equipment for producing makeup water. We shall be talking about demineralizers and other water treatment equipment in another module in this program. The problem of silica is so serious that in the event that we cannot reduce the silica content in boiler water, it will be necessary to reduce the operating pressure on the boiler and consequently the power output of the unit. So far in this brief review of boiler conditioning, we have looked at the effect of suspended and dissolved solids in boiler water, the need for chemical treatment of boiler makeup water and feed water, the control of boiler water concentration by continuous blowdown, the use of phosphate injection to prevent scale formation, the effect of carryover, which may be due to high solids content and high alkalinity, the effect of silica in boiler water, and the need to maintain concentration below established limits. Now, at this point, it's time for a break, and then we'll come back and look at the causes and ways to prevent corrosion due to boiler water condition. At this time, please switch off the tape and review this material in your workbook. Internal corrosion can take place inside boiler tubes under certain boiler water conditions. The corrosive action eats into the tube metal, removing iron and resulting in thinner tube walls. If this action is allowed to continue, certain tubes will fail and will rupture as the thinner section of tube can no longer withstand the internal operating pressure. The removed metal, products of corrosion, can also cause a problem, as this material now increases the total quantity of solids contained in the boiler water. As we know, this can increase the probability of deposits and scale formation on the inside wall of the tubes. So what are the conditions that cause corrosion and loss of metal inside the boiler drums and boiler tubes? Well, there are basically 3 independent causes of corrosion, and they are acid attack, which occurs when the boiler water is in an acidic condition, that is, low pH. Caustic attack, which occurs when the alkalinity of the boiler water is too high. The pH level is above about 10.5. the presence of dissolved gases such as oxygen and carbon dioxide in the boiler water. Let's first take a look at the problem of pH value. As we know, the pH scale runs from 0 to 14. It is really a measure of the hydrogen ions contained in the water mixture which forms the particular solution in question. The value of 7 is generally recognized to be neutral, with lower numbers indicating an increasing degree of acidity, while higher numbers from 7 to 14 indicate alkalinity. A highly acidic solution, such as sulfuric acid, for example, will indicate a pH value of about 3.5. Conversely, a highly alkaline solution, such as caustic soda, will probably indicate a pH value of about 11.5. Most natural waters in fresh lakes and rivers usually have a pH value close to 7, unless, of course, pollution is present. So if we are to prevent acidic corrosion inside our boiler, it is obvious that the pH value of the boiler water must be maintained above 7. Actually, to be on the safe side and to allow for the fact that there are probably variations within the mass of water, the normal established limits for boiler water pH are within the range 8.5 to 10.5. But what is it that actually determines the pH of the water? Well, this all depends upon the makeup of the contaminants in the water, such as magnesium sulfate, calcium carbonate, silica, iron oxide, carbon dioxide, and others. Most of these contaminants are contained in the feed water in very small quantities, of course, but the concentration builds up in the boiler. It's usually necessary to add alkalinity to the boiler water in order to raise its pH and bring it within the prescribed range. This is done by injecting sodium hydroxide. This is a highly alkaline caustic solution. Similar to the case of phosphate injection, a mixing tank and high-pressure feed pumps are provided to inject the caustic directly into the boiler drum. This injection of caustic does achieve the objective of raising boiler water pH value, but it also has some negative effects. One is that we are adding yet more solids to the boiler water. However, a much more significant problem is that too much free caustic in the boiler water may bring about concentrations that can cause cracks in the boiler metal. This is known as caustic attack or embrittlement. So we can see that it is not just low pH that we have to worry about. High pH is also undesirable. For this reason, we find that the established control limits for boiler water pH are often reduced to a narrower range, say 8.5 to 9.5. In order to keep within this range, it may be necessary to use disodium phosphate instead of trisodium phosphate. The objective is to feed less sodium into the boiler with resultant reduction in free caustic. In many plants, the control of phosphate addition and pH is guided by a curve like this. This shows the maximum pH level which should be allowed for any particular concentration of phosphate in the boiler water. For example, for a phosphate concentration of 4 ppm, the maximum allowable pH is indicated at 9.2. pH values above this level may lead to caustic attack at certain locations in the boiler. It may even be necessary to use monosodium phosphate in some cases in order to hold the pH level down to the desired level. This curve, known as the congruent phosphate control curve, is usually provided by water treatment specialists, and its actual design depends upon your specific boiler conditions, particularly the operating pressure. A common cause of corrosion in boilers is that due to dissolved oxygen contained in the boiler water. When oxygen is present, it causes severe pitting on metal surfaces, such as the boiler drum and water tubes. The oxygen enters along with the feed water and makeup water. Carbon dioxide, another dissolved gas, is also highly corrosive as it turns to carbonic acid. It is extremely important that the dissolved oxygen and other gases such as carbon dioxide be removed or at least reduced to a very small value before the feed water enters the boiler. This process takes place in the de-aerator, which is located in the condensate and feed water system. We'll be talking more about this equipment in another module in this program. The basic function is that the water is heated sufficiently to liberate and expel any gases from the solution. Modern de-aerators can reduce the dissolved oxygen content in feed water to about 10 parts per billion and even lower. However, because the effect of oxygen is so harmful, further chemical treatment is usually added after the de-aerator. The objective of this is to remove the remaining traces of oxygen and to protect against any failure of the de-aerator. In low-pressure boilers, sodium sulfite may be used, but the preferred oxygen scavenger today, particularly at high operating pressures, is hydrazine. The reaction of hydrazine and oxygen produces water and nitrogen, which is eventually expelled in the condenser or the de-aerator. The hydrazine is usually injected into the feed water immediately after the de-aerator, so that some reaction may take place before the feed water enters the boiler. Once in the boiler, some of the hydrazine vaporizes and passes over with the steam, moving through the turbine and into the condenser. Here it may help scavenge any oxygen that is present in the condenser. One problem with hydrazine is that it can be a health hazard, and therefore certain precautions must be taken in handling its feed system. Usually, the hydrazine feed system is completely enclosed to prevent any contact between operating personnel and the hydrazine itself. Alternative products are available to be used in place of hydrazine, such as hydroquinone, DEHA, carbohydrazite, and others. These substitutes are apparently safer to handle. We have just mentioned that hydrazine volatilizes. Other volatile chemicals may be used in place of phosphate and caustic injection, where the boiler operating pressure is above about 1500 psi. The reason for this is that at high pressure, we wish to keep the solids content in the water as low as possible. In many of these systems, the condensate and feed water system includes a polishing demineralizer in the feed train. This means that all of the feed water passes through the polisher for removal of virtually all contaminants. This eliminates the need for adding phosphate to prevent scale formation from dissolved solids. Moreover, we do not want to be adding solids in the form of caustic to our clean boiler water. So how do we, in this case, control pH value of the boiler water? This is where volatile treatment comes in. A chemical such as ammonia, morpholine, or cyclohexylamine is fed continuously into the condensate system, and this passes right through into the boiler. Once in the boiler, the material vaporizes and passes over with the steam through the turbine to be condensed into liquid once again in the condenser. This material circulates through the steam and water cycle, with makeup being added continuously. The effect is to raise the pH value of the water to protect against acidic corrosion in both the pipework and the boiler. Clearly, from our discussion here, we can see that boiler water conditioning is often a compromise, and it does require experienced water treatment specialists to establish the procedures for your particular boiler. Now, this will include the limits to be maintained of various constituents in boiler water, the type of additive chemicals to be used, and the correct mixing concentrations, the frequency and methods for performing analysis on boiler water and feed water, the methods for reporting results of water analysis. Most large power plants are equipped with specialized personnel and lab equipment to perform boiler water analysis and control. In smaller industrial plants, the operator may be required to carry out certain tests with backup from a visiting specialist. In many plants, continuous automatic analysis is performed and displayed on a panel. Of course, in order for the readings to be meaningful, it's essential that the equipment be regularly checked and calibrated. The operator must always be aware of the actual boiler water conditions at any time and how this compares with the established limits of operation. He must also know what action to take in case the conditions move drastically outside the limits. Be sure to check the procedures and established practice for boiler water control in your particular plant. For now, please switch off the tape and review this material in your workbook. Unfortunately, power plants burning fossil fuels do produce a number of pollutants, which can be harmful to the environment. Pollutants from the boiler discharge to the environment in three different forms. Emissions contained in the flue gas discharging from the chimney to atmosphere. Liquid effluents, such as wastewater from air heater washing. Solid waste materials, such as ash. During the plant design and construction stage, the engineers need to calculate the probable total quantity of pollutant discharge and identify the source of each individual contaminant. The plant design will then incorporate particular features to eliminate or at least mitigate the effect of these pollutants on the environment. Strict limits are placed upon the allowable concentration of pollutants which may be discharged from the plant. These limits are set by environmental authorities and enforced by government legislation. Compliance with the environmental regulation is essential in order for the plant to retain its operating license. The operating procedures, equipment design, and maintenance are all developed with these regulations in mind. Monitoring of critical discharges from the plant is performed on a continuous basis through the Continuous Emission Monitoring System known as CEMS. Regular reports must be submitted to the environmental authorities, and spot checks and audits are often carried out without prior notice. But what are these pollutants and where do they come from? Well, the source of most pollutants is in the fuel itself, as we'll see in a moment. The troublesome emissions contained in the flue gas include particulate matter, toxic air pollutants, sulfur oxides, that is SOx, nitrogen oxides, that is NOx, carbon dioxide or CO2, carbon monoxide or CO, hydrocarbons, vapor emissions. Let's take a closer look at the effect of each of these pollutants. First, particulate matter. Particulate matter consists mainly of fly ash and possibly particles of carbon. The pollutant is actually solid material, but it is usually considered as an air contaminant because it is part of the flue gas stream and it affects the immediate surrounding atmosphere. The result is irritation to the eyes, reduction of visibility, perhaps an impediment to breathing for certain individuals, and the soiling of clothes, cars, and nearby residences. The particulate matter may include certain toxic compounds which are formed from small quantities of metals contained in the fuel ash, such as lead, chromium, nickel, and others. This problem may be more severe if the boilers are burning municipal refuse and industrial waste. Let's now look at the gaseous components of the flue gas. Sulfur oxides, SO2 and SO3, will be present in the flue gas if the fuel being burned contains sulfur. The SOx is produced by the combustion of oxygen contained in the combustion air and the sulfur. When the SOx discharges from the chimney to atmosphere, it mixes with moisture, and as this cools, it may form sulfuric acid and contribute to acid rain. Acid rain may cause damage to plant life, rivers and lakes, and the aquatic life therein. It may also be corrosive to metallic structures, and in certain concentrations may even affect human beings. SOx is indeed one of the most harmful pollutants to be discharged from the power plant, and steps must be taken to eliminate or reduce these emissions. We'll be looking at mitigation of pollutants later in this module. NOx includes various nitrogen oxides which are formed during the combustion process by high temperature reaction between nitrogen and free oxygen. Both of these elements are present in the combustion air, and small quantities may also be contained in the fuel. When discharged to atmosphere, NOx causes irritation to the eyes and throat and may even cause respiratory problems in certain individuals. It is also thought that NOx affects the ozone layer and also contributes to the formation of smog. Another constituent of the flue gas discharging to atmosphere is CO2, carbon dioxide. Actually, CO2 is inert and is not harmful in the atmosphere, but it is thought that the presence of carbon dioxide in the atmosphere may contribute to the global warming trend, the so-called greenhouse effect. At present, there are no emission limits placed on CO2, but conceivably this may come at some future date. The flue gas may also contain carbon monoxide, CO, if combustion has not been completed in the boiler. Carbon monoxide is extremely poisonous and in high concentrations can quickly cause death in human beings. In practice, the quantity of CO discharged from power plant boilers is very small and becomes completely diluted by the other gases discharged and the atmosphere. The main purpose for monitoring CO in power plant flue gas is more a matter of efficiency than pollution control. The term hydrocarbon refers to unburned components of fuel, particularly oil or gas, such as one may possibly experience from a petroleum refinery or automobile. From the power plant, hydrocarbons are likely to include certain particulate matter, such as unburned carbon or fuel oil smuts. In some power plants, a large quantity of water vapor may be formed in the flue gas scrubbing process and is subsequently discharged from the chimney. This is often regarded as a sign of serious pollution by uninitiated observers. In fact, the vapor is quite harmless, and it can be reduced by heating the flue gas to about 250 degrees Fahrenheit as it enters the chimney. From what we've just seen, we can say that the most troublesome contaminants in flue gas, those demanding attention, are SOx, NOx, and particulate matter. We'll look at the means for controlling these emissions later in this module. Let's continue our study of power plant pollutants now by looking at effluent discharges from the plant. The sources of effluent contaminants are boiler blowdown, air heater washing and chemical cleaning, cooling water systems, water treatment plant discharge, FGD slurry, that is waste effluent from a flue gas desulfurization installation, stormwater runoff from coal piles, ash ponds, oil tanks, and other possibly contaminated areas. So what are the effluent contaminants that cause environmental problems? One obvious item is the value of pH. This should normally be within the range of 6 to 9. However, more important is the need to maintain a steady pH value in the river or lake. Even small changes may have a profound impact on the ecology, that is, the plant and fish life. The presence of oil, grease, and any other floating material may also damage aquatic life, as well as being undesirable from the point of view of appearance. Suspended solids contained in the effluent make the receiving body of water dirty and may also affect the color. Solids may also form sludge and settle in water channels. Traces of heavy metals, such as lead, copper, zinc, mercury, and others, may be contained in industrial effluents. In the case of a power plant, this may occur with stormwater overflow from the ash pond. Many of these heavy metals are classified as hazardous, as they are poisonous to fish and also to human beings. Rapid changes in temperature are also hazardous for marine life. Therefore, the temperature of effluent discharging from the power plant must be maintained within established limits. Now, at this point, having looked at the nature of power plant pollutants, we'll take a break and then come back and see what can be done about this problem. For now, please switch off the tape and review this material in your workbook. Well, let's now look at some of the methods used to control or at least mitigate the effects of power plant pollutants. First, we'll consider flue gas. The actual limits set on flue gas contaminants may vary between different localities, states, and countries. This table shows typical limits set for large modern power plants in North America. The emission of sulfur dioxide must be kept below an average rate of 2.5 pounds for each million BTU burned. In metric units, this is given as 1.075 kilograms per million kilojoules. For NOx emissions, the limit is set at 0.5 pounds per million BTU. The emission of particulates is limited to 0.1 pound per million BTU annual average. Another check on particulates is the measurement of opacity, here limited to 20% as an average. Other units of measurement may be used for flue gas pollutants. For example, in Europe, SO2 limits are set between 400 and 2,000 milligrams of SO2 for each cubic meter of flue gas. This is based on excess oxygen of 6% in flue gas. In operating the power plant, we find that SOx and NOx are usually measured in terms of ppm, that is, parts per million in the flue gas. For example, the NOx limit of 0.5 pounds per million BTU would be in the order of 175 ppm, depending on the precise amount of excess air being used. But this is enough about target values. How do we actually control the emissions? Well, first, let's take a look at particulate matter, which mainly consists of fly ash and perhaps some unburned carbon. In coal-fired boilers, a large amount of fly ash is produced, and the most common way to remove this from the flue gas stream is by installation of an electrostatic precipitator, ESP. An ESP, as it is known, is capable of removing 99% or more of particulate matter from the flue gas. The operation of the ESP depends upon electrostatic principles. The flue gas is forced to pass between electrodes which are charged at a DC voltage of about 50,000 volts. This high voltage causes electrons to flow from the negative electrode through the flue gas to the positive electrode, which is grounded. The resultant electrostatic charge on the dust particles causes them to collect on the positive electrode, which is actually built in the form of a large plate known as the collector. Multiple collector plates are built in line with the gas flow and fixed solidly to the frame and outer box, which are all grounded. The negative electrodes, often known as discharge electrodes, are located between the collector plates in the gas passage. The high-voltage DC supply is obtained from transformer rectifier units, which are usually mounted on top of the precipitator. At frequent intervals, the plates and electrodes are mechanically wrapped so that the removed dust falls off into the collection hoppers below. The ash hoppers are not designed for storage, therefore the ash must be removed almost on a continuous basis. The main problems causing loss of collection efficiency in a precipitator are high resistivity of the fly ash as a result of burning low-sulfur coal, the existence of very small particulates below 0.3 microns in diameter. These problems can be overcome by installing a fabric filter instead of the ESP. The fabric filter simply blocks the passage of particulates and therefore is not affected at all by the resistivity of the fly ash. In fact, its efficiency of particulate removal is greater even than the ESP. Actually, it is not so much the fabric itself which blocks the passage of particulates, rather it is the layer of ash cake which builds up on the surface. The filter material is arranged in the form of a very large number of long bags, which are replaceable. The inlet gas flows upwards on the inside of the bag and passes through the fabric. As the inside of the bag becomes plugged, the pressure drop increases and the bag is cleaned by mechanical shakers. Means are provided to isolate sections of the filter so as to provide cleaning of some bags while the remainder of the filter continues in service. The pressure drop across the fabric filter, or baghouse filter as it is known, is quite high, about 6 inches water gauge, as compared to 0.5 inches for the precipitator. This means that larger ID fans are required. One important point to know is that the fabric filter is not suitable for use with oil-fired burners. This is because the sticky nature of the particulates, in this case, makes cleaning of the filter bags extremely difficult. Well, now let's move on to take a look at flue gas desulfurization. Of course, the most simple way to reduce the sulfur content in the flue gas would be to purchase a fuel with 0 or very little sulfur content. Unfortunately, this is quite difficult to arrange and also quite expensive. So we are left with the problem of removing the sulfur from the flue gas stream. This is done by applying a chemical reagent. The most common reagents in use today are lime and limestone. The main ingredient in lime or limestone is calcium. When this mixes with SO2, it forms calcium sulfite in the form of solid particles which can then be removed from the gas stream. Various methods are used to bring the reagent into contact with the flue gas so as to allow SO2 absorption to take place. In the dry method, the lime as a fine dust is blown into the flue gas stream at various injection points. The particles of lime pass along with the flue gas and attach themselves to the fly ash. Reaction with the SO2 takes place to form calcium sulfite, and this solid particulate is captured along with the fly ash in the precipitator or baghouse filter. Although this system is relatively simple, its absorption process is not very efficient, so the consumption of reagent lime is extremely high. However, this system may be utilized on small boilers if the target for SO2 removal is limited to about 60%. The most common type of FGD system installed today uses a scrubber, that is the wet limestone process. The essential feature of this process is that the reagent is mixed with water and the resultant slurry is injected into the flue gas stream. The chemical reaction takes place in a specially designed absorption tower. The tower is located after the precipitator so as to eliminate interference in the chemical reaction from some of the constituents in the fly ash. Of course, the ID fan and perhaps additional booster fans must be designed to cope with the pressure drop across the tower. As the flue gas flows through the absorber, it mixes intimately with the calcium spray, and SO2 is extracted from the gas. This is absorbed into the liquid, forming a calcium sulfite slurry at the bottom of the tower. The heaviest concentration of this slurry is continuously removed and processed. In most systems, this waste slurry is dewatered with the liquid being recycled back to the FGD system. The remaining calcium sulfite sludge is then chemically stabilized and packed into a landfill on site. In many locations, the calcium sulfite sludge is converted into calcium sulfate by oxidation, and this is then used to make gypsum for the production of wallboard, that is a common construction material. Clearly, we are only dealing here with the fundamentals of FGD. The subject is demonstrated in much greater detail in some of our other programs, such as environmental protection control. The subject of NOx control is also dealt with in that training program. The reduction of NOx in flue gas is generally achieved by modifying the technique and control of combustion. The main objective of low NOx techniques is to slow down the rate of combustion. This reduces the temperature of the flame, with consequent reduction in the reaction between nitrogen and oxygen to form NOx. One way to achieve this is by reduction of excess air, but as we know, this may result in incomplete combustion. To overcome this, special low NOx burners are installed. These are designed to allow far more precise control over air and fuel distribution to each individual burner. Over-fire air is often added at a higher level in the furnace to help complete combustion from low NOx burners. Another technique is to use gas recirculation, similar to the arrangement for temperature control mentioned earlier. In order for these low NOx techniques to be successful, the boiler instrumentation and control system must be more complex than on earlier boilers. Precision and reliability are vital. Where emission limits are extremely tight, a chemical method is sometimes used to remove NOx from the flue gas. One method is to inject ammonia into the gas stream. When temperature conditions are right, about 1600 degrees Fahrenheit, the ammonia reacts with the NOx to produce water vapor and nitrogen, which passes harmlessly up the chimney. This process is known as selective reduction. Because of the need for high temperatures in order to ensure good reaction, the ammonia injection nozzles must be located in the superheater or reheater zone, an inconvenient location. To overcome this problem, a catalyst reactor may be fitted into the gas stream, usually after the economizer, and this allows the NOx absorption to take place at lower temperatures, say 600 to 750 degrees Fahrenheit, or about 400 degrees Celsius. This system is known as SCR, catalytic reduction. Let's now turn our attention to the cleanup required for liquid effluent. Typical limits set on discharge effluents indicate that suspended solids should be limited to an average value of 30 ppm and 100 ppm maximum. The pH value should be between 6 and 9. Oil and grease must be limited to 20 ppm maximum. The residual chlorine must be kept below 0.2 ppm maximum. In order to comply with these limits, it is necessary to remove offending solid material from the effluent, and this is done usually by clarification and/or filtration. Most of the solid material is removed and must in turn be buried in a certified landfill site. Before the final clean effluent is discharged into the river or lake, the pH will be corrected by the addition of caustic or acid. One particular nasty effluent has been addressed in the regulations, and that is the seepage of rainwater down through coal piles or ash piles. This water, taking with it contaminants, some which may be hazardous, percolates down through the earth. There it may find its way into the natural groundwater, which is often used for drinking by animals and people. Nowadays, it is necessary to install an impervious liner, usually of heavy plastic, below any of these areas, including the ash pond. Stormwater runoff must be collected and treated to remove solids. A liner is also required for the landfill area where solid waste is eventually laid to rest. In fact, there are definite rules and regulations which govern the construction and operation of a certified landfill site. Now, in these last two segments, we've endeavored to briefly outline some of the environmental problems that face us in operating a fossil-fired power plant. We've been talking generally, but you must make sure to study your own plant requirements, its specific problems, and the established limits of discharge of pollutants. You may also find it beneficial to refer to our Environmental Protection and Control training program. At this time, please switch off the tape and thoroughly review this material in your workbook.